Okay, hi everyone. So we now continue to the software quarters 2 familiarization with the software. All right, so here is the software. Okay, Altera quarters 2 version 13.0. Right, so we have the option file right here. Okay, so if you want to create project, okay, normally we use new project wizard. Okay, new project wizard. So I will go to that after this. So we will first explore the features of the Quarters 2. Okay, we have hierarchy view, we have the tab of file. We should be able to see it after this once we have created the project. Okay, design unit and so on. So in this flow, okay, flow window, you will be able to see list of steps. Okay, compilation, early timings estimate, gate level simulation, RTL simulation, and full design. So normally we choose full design to see the full design flow of your RTL or FPGA design. Okay, so the full design until, if we scroll further down, we should be able to see until generate programming file. So whereby our programming file during this step ready for the FPGA configuration. So FPGA configuration is under this one, program the device. Okay, um, from now this flow is not yet available because we not created any project. Okay, so first we need to create a project. So to create a project, we can also use this. Okay, open new project wizard or open existing project. So for example, you already created that project, so you want to open it again, so you just use this option. Okay, for our case, we start with open a new project wizard because we want to create a new project. Okay, double click on it and it will bring you to the wizard. Okay, so here is actually explanation. This project wizard helps you to create a new project and preliminary project settings, including the following: project name, directory, name of the top level design of your entity. So remember, design entity, project files and libraries. So we have, if let's say we have multiple files in our top level design, so it will be listed here. Okay, target device. So in our case, we will be using Cyclone 2 FPGA. Okay, and EDA tool setting. Right. So just follow the step next, and here is actually the working directory of your project. So you can either use the default location or you can choose the other location. For example, you want to go to the other drive. For example, we move to drive D, for example. Okay, and then you go to download, for example. This is just an example. Okay, okay, or you go to the other folder. Okay, work D Altera, and then you wanted to create a new folder. For example, you give the name of your course. So NMJ 32303. Okay, now you have that folder, and then you click on this and then you select the folder. So now we move to that particular folder, meaning that your raw file, okay, will be available inside this, and including your all the computer generated file. So let's say you want to make another folder that will specifically focus to your task. For example, you want to make a multiplexer, for example. So you just type here marks. Okay, although this folder is not yet created, it will be automatically created for you. Okay, other than manual step, we can also use this way. Okay, so the name of the project, so this is very important. The name of the project must be the same as the entity name of your top level design. Okay, so for example, we give it as marks, MUX marks. Okay, marks 4, for example, marks 4. Okay, marks 4 is okay, but don't start with this one 4 marks. So this is not um, cannot be used lah. Okay, not allowable. So you can use either marks 4, okay, or marks underscore 4, but not mark white space 4. White space is not allowed. Okay, it's not allowed. So marks 4 is okay, just nice. Okay, so just to represent your, we are going to to design a multiplexer. Okay, with 4 input, for example. Okay, next. Okay, so the dialog box will pop up telling you that the marks folder here is not available or not yet exist. So do you want to create it? Just say yes. So it will create automatically for you, right? So this page, if you have already written the design file, you can add from this menu. Okay, if you don't have, it's okay. You just click next. Okay, so during this page you're going to select the device that you're going to use for your FPGA. Okay, so remember we going to use Cyclone 2 FPGA, and we have a lots of devices here available. So you choose the one that available in our lab. So if I'm not mistaken, the device is EP2 C70. Okay, okay, I think this one. Okay, EP2, 2 stand for cyclone 2. Okay, C70 is actually the 70 means that the number of logic element, okay, is about 70k. Okay, you see here 68k, so it's about 70k. And okay, and the rest is actually the speed of the processor or the FPGA. And then you click next, and this is actually a EDA tool setting. So in our case we will be using the simulation tool using the Altera module sim Altera, and then in Verilog format. Okay, right, so click next. Okay, and then this is a summary. So your project directory will be here, and the project name is marks 4 and top level design entity. So please take note on this, very important. Marks 4, so the names marks 4 has to be the same as your design entity name in your Verilog file. It has to be the same name, and also small capital letter, right? Small letter, sorry. Okay, so this is actually the family, the Cyclone 2 FPGA with the device number EP2C70F896. Okay, this is, you can check in the Altera board, lah, right? Okay, you click finish. Once you click finish, you now already created the, you go to tab hierarchy, and then you should be able to see the project name as marks 4. We not yet created any design file. So when you double click, it's mentioned to you, can't find design entity mark. So what we need to do, we need to create the design file. So we go to this one, okay, new, or you, or file new. So either one, okay, to be easier, just click on this. So choose Verilog. Okay, this is in order to design, to create our design. So Verilog HDL. So we have a lots of design entry, okay, AHDL, block diagram, and so on. So including the VHDL, don't choose VHDL, choose Verilog HDL, because we're going to write using our design using Verilog HDL. Then you click on OK. So now this is actually unnamed file, verilog.1, not yet named as marks. Okay, so you can now start write the coding of our of your design. Okay, so normally we start with module. Okay, so module, okay, enter, and then we end it with end module. That's actually the basic step. Okay, so next we give the entity name, which is MUX4. It has to be the same entity name as your project file, and also your file to be saved lah. Okay, right, project file is okay. Your the file that you're going to save has to be the same as your entity name. So you can save and copy, and then you click on save. Make sure you tick on this add file to current project, and then this is the file name. Okay, make sure it's same name as your design entity. Okay, now it's saved to your working directory marks, and then you save it. Now we should be able to see the names is now replaced to marks4.v. Okay, now we can start write the code. Okay, so for example, we're going to design a multiplexer with 4 input. So we have marks4, and then we open bracket and close bracket, and then you put this way, okay, semicolon, and then you enter. So this is actually Verilog version 2001, whereby we declare the input together with the um, direction of the input, and also the size of the input or output data with. Okay, so for example, we have 4 input A, B, C, and D. So this is actually sharing the same size of data width, which is 1 bit. If you don't specify here, means that it's 1 bit, okay, and the A, B, C, and D is actually the input. Okay, put comma here in order for us to give another input, which is selector. Remember, in our class multiplexer need to have a selector to select the input. Okay, so how many bits to select the 4 input? So as we discussed in the class, so for 4 possible combination of input, we need to have at least 2-bit selector. So 2-bit selector in Verilog represented using this way. So 1 to 0. Okay, 1 to 0. So that's actually the size of the data width for the input. And then you can give the name as selector, for example, and then you comma again. Okay, interesting to see here, line number 2 and number 3. So A, B, C, D, and also selector, these are the input. Okay, however, selector got different size of data width, and that's why we need to declare it separately, okay, compared to input A, B, C, and D. Okay, A, B, C, and D only 1 bit, whereas selector is 2 bit. All right, so what's next? Okay, so you go for the output. Okay, output. How many bit is the output? The output is just 1 bit. So you just give any name, for example, out. Okay, and then you're done with the declaration of the I/O together with the data width. Okay, so if you want to put the comment here, so we can put I/O declaration. Okay, so if you want to put a comment, so I repeat again. So you put 2 / like this one. So line number 2 now become a comment. Okay, it's not going to be evaluated by the compiler. So the compiler will ignore line number 2. And that's why we need to have at least 2 / to tell the compiler that no need to evaluate or compile that particular line. Okay, which is line number 2. Okay, we finish on IO declaration. So now we're going to what we call to write the body of the program. Okay, so the multiplexer, it works as a selector. Actually, it will select either A, B, C, or D. So that's actually the functionality of the multiplexer to pass as an output to the output port. So it's depending on the selector. So for this case, we can use many ways to write the coding. For example, I maybe shows you using um, um, a standard way, a standard and a simple way to write the code. Okay, we can either use data flow techniques, or using if else, or using case statement. Okay, so let's say we use data flow techniques. Okay, so data flow, this is a straightforward technique, but you can see that it's a bit tedious, huh? Okay, so to use a data flow technique, so I make it simplified. Okay, so this is actually the data flow. So the data flow is comes from the truth table. So this technique is not a good technique. Okay, it's okay. We start with the simple one. Okay, because it's error prone, because sometimes you might miss the tilde and so on, and you will not actually understand what actually um, the line of code's meaning. Okay, it's based on the data flow concept. Okay, another technique, we can use the if else statement, which give you better what we call better understand. You will understand the technique. Okay, so we can comment this. Okay, comment in group. Okay, and then we use another technique that is called as if else, behavioral if else, if else technique. Okay, so in if else technique, we need to use the always block. So don't worry about this, we will learn in the lecture. So always add all the input, all possibilities of input. So that's the rule. So always add A or B or so, or C. So all the input, or D, A, B, C, D, or cell. So cell also adds an input. Okay, once you finish this, you put begin and then end. So this is actually to mark the beginning of the block. So this is actually another block, one always block. We call one always blocks. Okay, instead of the big module and end block or entity block, so we have another sub block we call as always block. So inside this always block, we will start write a coding that explaining or describe the behavior of the if else. So if selector selector equal to, so remember this, equal to what? Equal to 0. Okay, our output will become A. Okay, then else if, okay, else if selector equal to 1, our output. So please use a tab to make your code is readable. Equal to B, okay, and so on. Okay, you can make it until the rest. Okay, we have selector equal to um, 2 equal to C. Okay, and then you select else. Okay, output equal to D. Okay, that's actually the body of your multiplexer. So normally here I can either put this way or put 2 prime um, B00. Okay, and then this selector 2 prime B01 to see the pattern, and then 2 prime B 10. Okay, you see for the 2-bit selector, I can put comment here as well. So we have 00, okay, 01, 0, 10, sorry, 10, and 11. Okay, so now we have 00, 01, 10, and 11 is under else. So we can put another comment for the case of selector equal to 2 prime b 0, sorry, 2 prime b 11. Okay, so now we have finished this. So another thing that you need to remember, because inside the always block, any left side hand element, so this is actually the rule. Okay, any left side hand element of the always block, we need to have to be a register data type. So out here is actually the what we call left hand side element. So we use the equal sign as the divider. So those on the left, in this case out is actually the left hand side element, has to be a register data type, and therefore we need to put reg here. Okay, So let's say we don't want to put rack, so it will be default to wire. So when we run the simulation, you will get error. So let's say you want to see the error first. So first, you can save, or you just click start compilation, and it will ask you whether you want to save it. Yes, click yes, then it will run the simulation. So we will get the error. Okay, and then six error with one warning. Okay, okay, don't worry about it. You go to the tab error, okay, and see a lots of error here. Don't worry, you just double click on the first error here. So it mentioned you line number 19 of the design marks 4. So this is the design marks 4.v. Line 19, object out. So as I mentioned to you, the left hand side of the assignment must be a variable data type or a register data type. So we need to put rect here. Okay, once you put rect and then you recompile again, then say yes, and then the error gone. That's actually the tips and tricks how to uh, do the debugging process. Okay, so now we are in the process of creating our design and compiling our design. We wait for the compilation to finish. So successful with 12 warning. So we go to the tab warning. So just check the warning whether the warning related to your design or not. So in this case, none of the warning mention your marks 4.v, your design. So means that you can ignore the warning, right? Okay, so now this is actually the flow of your design, what happened and so on until up to the level that you finish right now. So if you go to the flow, full design flow, we can see that the green tick here means that we have now until the analysis and elaboration, and also we should be able to see the RTL, okay, because we already finished the filter. Okay, this is actually the design flow. So we are ready, okay, until the implementation, before the pin assignment. So pin assignment is somewhere here. Okay, we will talk about the pin assignment in the next video. Okay, what's the most important thing here? We want to see the RTL. Okay, so here we have the Rtl viewer. So under the analysis and elaboration, you go to Rtl viewer. And now you should be able to see the hardware that I mentioned in the class. So this is actually the hardware or the multiplexer. Okay, we have four input: A, B, C, and D, and we have one selector. So all of those on the left hand side is actually your input, and those on the right hand side is your output. Okay, as I mentioned to you, we coding at RTL level, and that's why we didn't see any logic gates here, or even small lower level of representation of circuits, because this is at RTL coding. We just see the register transfer level view. Okay, so this is actually your hardware. Okay. You can go to viewer option, and then you can change the view option to different lah. Okay, different view. Okay, we're not going to cover here now. So we just to want to show you the coding is now synthesizable. Synthesizable means that you're able to see the equivalent hardware without any problem with the connection, whether connection at the input or the output. You see all connected. Okay, all right. So you can stop this one, close this one, okay, and then you are now finished with the design. Okay, I think this is all for the today's video. Keep subscribe the channel to get more updates on the next video. All right, that's all for today. For now, thank you and see you on the next video.